class. In today's lesson, we are going to be talking about how we can use the value of electronegativity to determine the type of bond that will likely form between any two atoms on the periodic table. So when we left off, we had discussed ionic bonds, polar covalent bonds, and non-polar covalent bonds. And we had mentioned that you could tell the difference between them by looking at the difference in their electronegativity. So there are two things that I need to tell you before we move on from here. The first thing is that electronegativity is a value measured out of a score of 4. The most electronegative element on the entire periodic table, which is fluorine, has a value of 4, and everything else has something less than 4. The thing that I need to remind you is that when we say the difference, we mean subtract. So what we're going to be doing for this is we're going to be looking up different electronegativity values on a chart or on a periodic table, and then we're going to be subtracting those values to get the difference, and then we're going to be using the difference to tell us whether the bond that was formed is ionic, polar covalent, or non-polar covalent. So now you're ready to go. Let's get going. So once we've subtracted the two electronegativities, we are going to put the answer onto a number line that looks like this. If the value is between 0.4 and 0, the difference between them, then we would indicate that that bond was a non-polar covalent bond, meaning that the two atoms had pulled evenly on the electron. If the difference between the two is 1.8 to 0.4, okay, all the way up to 1.8, then we would call that bond polar covalent bond. And if the value is greater than 1.8, really greater than or equal to 1.8, we would call that an ionic bond. So up here it says that an ionic bond is greater than 1.7. Down here it says 1.8 and above. Those are the same thing, right? Greater than 1.7 is 1.8. So greater than or equal to 1.8, which is greater than 1.7. That's a question for your math teachers. You can roll on over there and ask your math department if you don't understand what I just said. So once we get the subtraction problem answered, we're going to go back to this very chart to determine whether the bond is ionic, non-polar covalent, or polar covalent. So let's make sure we get this chart somewhere that we can use it for reference. So now that we have this chart up here, we're ready to get going with some example problems to see how we might use this in real life. So this is a periodic table that has on it a whole bunch of different electronegativity values. You can also find these electronegativity values in your textbook. You can see that the ones with the highest electronegativity are over here. Fluorine, oxygen, chlorine, and nitrogen have very high electronegativity values. The lowest are way over here on the bottom. Rubidium and strontium have very low electronegativity values, and the trend shows us that we go up and to the right on the periodic table. When we're going to try these problems, we're going to put the larger or the higher electronegativity value first on the chart. So we're going to do a problem where we look at hydrogen and fluorine. So what I'd like you to do is look in your textbook or look back on the previous slide and find the electronegativity values for fluorine and for hydrogen. Fluorine's electronegativity value is 4. We know that the trend for electronegativity takes us up and to the right. Hydrogen is here, fluorine is there. We already know that fluorine is going to have a higher electronegativity, so I'm going to put fluorine's value first. 4.0, that's for fluorine, minus the value for hydrogen, which is 2.1. Again, I'm looking up these values. You might be Googling what is the electronegativity value of fluorine or what is the electronegativity for hydrogen. You're going to be looking them up. So when we subtract these two, we get 1.9. So if we go back, so first of all, we get our values here. And then if we go back and we look at our table, 1.9 is here, so this is an ionic bond. So we have determined the type of bonds by first subtracting and then determining the bond characteristic. So let's do the same thing, this time for sodium and chlorine. So again, chlorine is over here, so we're going to put its electronegativity value first, which is 3.0, minus the electronegativity value for sodium. Sodium is much further over here, and sodium's electronegativity value is 0.9. So when we subtract those two, we get 2.1. Also an ionic bond, right? 2.1, somewhere over there, ionic. So again, we've used the difference in electronegativity, the difference, which is the subtraction, to determine the characteristic of the bond. So let's do just one more. We're going to look at hydrogen and hydrogen. So hopefully you can kind of imagine how this might go in your head already, but we put the electronegativity value for hydrogen, which is 2.1, and we subtract the electronegativity value for hydrogen, which is 2.1. And we get 0. 0 is here. So this bond is nonpolar covalent. We had indicated that the idea was that a nonpolar covalent bond was often when an element was fighting with itself, right, evenly matched for that electron. And so obviously if their electronegativity values are exactly 2.1, they would be pretty evenly matched. This is a good time to remind you that electronegativity is the strength of the atom, its ability to pull the electron to itself within a chemical bond. So in this case, we are looking at the matchup here, okay? How does chlorine compare to sodium when they both pull on that bond? Well, chlorine is going to win handily. It's going to get the electron totally away, so it's going to form an ionic bond. How is hydrogen going to compare to hydrogen? Well, they're going to be locked in a stalemate, no one with the upper hand, and so they will have that even share of the nonpolar covalent bond between them. We're going to look at two more examples, magnesium sulfide, MgS, and we're also going to look at CO2. We're going to learn something new when we look at CO2, so make sure you're paying attention for that one. So for MgS, we go ahead and we look them up again on the periodic table or in a chart in your book, and we find that sulfur is 2.5, where magnesium is 1.2. So when we subtract these two from each other, remember you get to use a calculator for this, so you should be good at doing this. We get an answer of 1.3. And at 1.3, we are in this area, so this is a polar covalent bond. For something like CO2, very important here, we cannot do both oxygens at the same time, so we can only look at a bond between C and O only. So when you have a subscript like that, you can kind of leave it out of your calculation, which, spoiler alert, is going to be on your test. So when you see the subscript on your test, do not include it in the math to find out the type of bond that you're looking at. Oxygen is our more electronegative atom here with a value of 3.5. And oxygen has a value of 2.5, and so we get a value of 1 when we subtract them. And once again, putting me in the polar covalent bond. So there we have our extra examples for how we might solve different types of bonds based on the difference in their electronegativity. Great job, guys.